All right, so
Takes longer than known to find lights over there.
okay, so what we've done up so far, I spent the first half hour just catching up on the forums. That middle half hour, we went through and looked at human energy consumption and human power. Later in the course, we're going to get into focus almost exclusively on technological power. So we'll go through each of the technologies, but that's just to start wrapping our heads around the difference between energy, power, time, and putting some numbers down. I could tell when you guys were working the problems, like you're getting really big numbers, really small numbers, but really the point of that is to realize, a human power, it's not kilowatts, it's not terawatts, it's just about 100 watts. So it's a good benchmark kind of number to keep in your back pocket. Same thing with that 10 megajoules per day. And so as long as you can kind of keep those two numbers in perspective, a lot of the other big numbers we're going to talk about will sort of fall into place and have some meaning. All right. While we're on that topic, I wanted to give you a little preview into Summary 1. The paper is here. You can just grab it. This was my first publication in renewable energy, sustainable energy. My main motivation for writing this, I've been obsessed with efficiency kind of forever. I think every person kind of has their own obsession, passion, or whatever. For whatever reason, I've just been obsessed with efficiency, how things move, how energy gets used, created, destroyed, what have you. And it wasn't until, gosh, I don't know, about this long ago, maybe 10 years ago, I first started writing the paper kind of at the height of the Gulf War. And it became a big question in my mind why we had to send American troops halfway around the planet to defend oil wells. It just didn't make much sense to me, especially I'm pretty passionate about riding my bicycle. I see it as a great way not only to maintain some physical fitness, but save time and frustration with parking, and it's a good adrenaline rush. And I think we'll see shortly that a human running at 100 or 200 watts is many times more efficient than your automobile running at thousands, if not tens of thousands of watts. So in my mind, I'm like, why can't we just be more efficient? Why don't we just put up solar panels and wind turbines and just be done with all this fossil fuel, monkey business, war for oil, et cetera, et cetera? So my approach was to take an engineering approach rather than a political grandstanding, et cetera. And it was a big eye-opener for me. And I really wanted to write a paper that would be accessible kind of to the lay person. I did a lot of reading of Carl Sagan growing up. I don't know if you've heard of Carl Sagan or not, but he was, a very well-respected physicist, quite good in his field, doing a lot of things with NASA. And he ended up catching a lot of flack from his kind of hardcore scientific colleagues for, actually trying to reach out to the public and make science more accessible. That was also my goal in this paper. I'm not sure I was all that successful because even here in the abstract, there's a lot of numbers and jargon that frankly 9 out of 10 or maybe even 99 out of 100 people just are not familiar with. So I think as soon as you start seeing things like this, gigajoules, and even here in this classroom, I don't think any one of us could tell you exactly what a joule is yet. A billion of them, I don't know what the heck that is. I think we have a pretty good estimate, though, with that 10 megajoules. I think you could say, okay, well, that's 10 million joules. But it took us a half hour or an hour just of focus to get our own little heads wrapped around that because we care about it. Most other people are like, I don't know, as long as my car starts in the morning, my coffee's hot, that's fine. But the big eye-opener for me really was to see just how much more energy dense oil is than a bucket of photons. So if we're looking at, and I'm just going to use a cubic meter, so a cubic meter is about half of the volume of your fridge. A cubic meter is a standard volume. And so if you put pure oil into 1 cubic meter, you've got 35 to 45 billion joules of energy, depending on the quality or the grade of oil. Now, if you compare that to solar energy, and just imagine taking that same cubic meter and just walking outside right now, and whatever radiation is sort of bouncing through that, how much energy is in there? Well, gosh, it's 1.5 microjoules. It's 1.5 millionths of a joule. And I think, let's see, so if we, a little later, let me scroll down in the paper. I thought, you know, when I first started looking at this, typically when you see solar power being rated, it's rated in watts per square meter, right? Normally you don't think of a bucket of photons. You think, okay, I've got a certain size on my roof, how much power is flowing through that area, not volume. But, you know, the photons, I mean, they're traveling at the speed of light, but they have to be somewhere at some point in time. At some point, let me just find the kind of the mind-blowing. Okay, here we go. I've got it down there somewhere. Okay. Oh, I guess with this guy, I was just trying to show what a millionth is. And again, I was just kind of trying to reach the layman and show that there's this little white dot here inside of the black circle, and the black circle is sort of sitting at the edge of this gray circle, which is here. So the tiny blue dot, and it looks white, but originally it was blue, is 1/10,000th of this, so 10 to the minus fourth. And the black one is 1/100th, so you could imagine 100 of those black guys sitting inside there. So thus the blue dot is 1/1,000,000th of the area. The energy density of solar radiation is 1/1,000,000th of the dot. The point is, let me actually just do the math here instead of blabbing on. So if we take so let's do oil. Oh, shoot, my not. Huh. The pen's not working. Oh, maybe it is. Hang on. Well, I'll type it out. So oil equals 35 billion. This is joules per meter cubed. Sun equals 1.5 microjoules equals 0.000. Let's see, that would be a tenth, hundredth, thousandth, 5, right? So there's 1, 2, 3, 4, 5, 6. And this is micro. That little funny looking m, it's a mu for micro, 10 to the minus sixth. Same units here. Make this a little bit bigger. Okay. So now if we're going to, we'll just say oil over sun. Now, I don't mean the energy density of the sun. We're not digging into the sun and grabbing a fusion process directly. This is just sunlight. LIGHT, oil over sun equals, so let's look at 3.5 divided by 1.5 times, and now we've got 10 to the, what is that, 10 to the 10th divided by micro 10 to the minus 6th. Now I'm gonna hop into Microsoft Excel because I know that funky little calculator that's built in does not have the number of zeros is going to be too many. So let's just run this through Excel and say equals 3.5 E10. So the way to make exponential in Microsoft Excel is just to say E10. So 3.5 times 10 to the 10th divided by 1.5 E minus 6. So I'm just dividing I'm dividing the very big number by the very small number, so I'm going to get an even bigger number. All right, 2.23 times 10 to the 16th. And that's just hard to think about. 2.3 times 10 to the 16th. Now, let's do this. That's going to be 23 times 10 to the 15th. Same thing. All right, and now, oops. Let's just run this and say 1,000 is 10 to the 3rd, a million is 10 to the 6th, giga or a billion is 10 to the 9th, tera is 10 to the 12th, peta, yeah, there we go, 15th. So oil is 23 petatimes greater energy density than sunlight. And so right away you can say, well, gosh, yeah, now I get it. Now I can see why that energy resource is that much more valuable. It's just sitting right there ready to use. And the numbers were not, they were mind-blowing at first. It's even a greater discrepancy than that 10 million to 1 ratio that we looked at 2 days ago. You know, we're extracting that energy 10 million times greater than theirs, but it's actually 10 to the 15th times more energy dense. So it's kind of it's a win-win across the board for the petroleum industries.
So energy dense means just how concentrated?
Yeah, it's exactly what it means. So even in class of secondary, we were talking about that T-bone steak, and so you're not going to eat the bone. I mean, maybe you could get some calories out of that if you processed it properly. There's going to be some energy in the protein. There's also going to be some energy in the fat. The fat itself is more energy dense than the protein. So pound for pound, there's more calories in it. That's exactly what it means. And in terms of density, you could do it on a per mass basis, like we did with the steak. In this case, we're doing it on a per volume basis, per cubic meter. So those are the numbers. Okay, so that's the paper you're going to read for the summary. Let's now look at the chapter just a little bit. And this, I don't want this to be the kind of course where I'm just reading out of the textbook to you and all that. The textbook's there it's great, but let's just thumb through it a little bit here. We were just talking about oil, so this is an appropriate figure to examine. And the takeaway here really is that the price of the oil has something to do with the technologies involved in extracting, but not as much as you might think. A lot of it's social, a lot of it's political, a lot of it's just based on stability in the regions where this stuff comes from. I've got a book there in my office called Petro Warfare, and one thing I think that most Americans don't realize is that Saddam Hussein actually started making agreements to sell his oil in euros rather than the dollars. And it was sort of the unspoken international truth, law, what have you, is that all international transaction for selling an oil was to be done in dollars. As soon as he decided not to, his days were numbered, basically. And then you can sort of see what the result was. It's estimated that Iraq has approximately 10% of the world's remaining oil reserves, and that's where the U.S. had invested a lot of its infrastructure. You can see why there's an economic incentive for maintaining control of that. And this was more or less the Arabs realizing that they had a monopoly, and as soon as that they could potentially have a monopoly, as soon as they did, they created an artificial shortage, and there spiked the prices. Another part of it is Iraq is right there. I mean, it was more or less, the entire country was more or less engineered as a way to get oil out of the ground after World War II. Okay. Probably also remember that the title of this course is Sustainable Energy Systems. So we'll come back to this very, very simple figure many times, but you could look at just about anything. Even our human energy example a second ago, you could take your body as that system. I mean, your body is that little potato there. Food comes in, waste products go out through the boundary, and that ends off in the environment somewhere. And so you're exchanging matter and energy with the environment. That's true in our own organisms ourselves. It's also true in all the power technologies that we're going to study throughout the semester. So here's a nice little overview of the book. There is one chapter on renewables, but for the vast majority, it's focusing on these non-renewable supplies. So there's a little bit about what the supplies look like. Here's how it gets out to the public, industry, manufacturing, and then here's what it's used for. And this is pretty standard. You'll see this same type of division in Amory Lovin's text as well. So there's nothing unconventional about this. This is a lot like that problem we did on Tuesday. Here I mentioned 1865 as Titusville, PA. This is the tail of the left tail of a bell curve. What this future is going to look like, we'll see. I mean, we're writing it right now. You can see these other energies coming online. When I was just at the Clean Coal Conference in Billings last week, there was a scientist there from the DOE, and rather than having this in joules, you can see that's exajoules, that's 10 to the 18th, he just had it in terms of fraction or total energy consumed, and this entire quadrant was just wood. That's all it was. I mean, that's where all of the energy came from before there were all these things. And I don't even know. Oh, here's your biomass, right? So this is sort of biomass. So rather than showing the absolute values, you can see that that's more or less what it was. Mainly just wood, sort of as far back as you care to go in humanity. Here's world population. We're gonna focus a lot on this in summary 3. We'll also we've got another paper where we'll look at energy consumed per capita. And, you know, a big theme here is how do we sustain our quality of life with less energy? How do you, you know, make your buildings more energy efficient and turn to sources that are in fact renewable and just use what we got a little more wisely. This is GDP. Frequently, it's shown that countries that use more energy have higher standards of living. Not surprising, like better travel, better entertainment, better food supply, et cetera. But, you know, as these global sources dwindle, it's going to get interesting in terms of, you know, sort of global average quality of life. No surprise here, you can see that the non-renewables dominate, and hydro is more or less tapped out across Earth. It sounds like China is going to make some gigantic dam in Ecuador pretty soon, which is, I don't know, the best news, but it's happening. But you can see in these other sources, it's still pretty small, and I think this is globally, and it varies country by country. In the United States, it might be as low as 1 or 2, but that's good news for the renewable energy technologists because it's only going to grow. It's only going to get bigger. I think this is a shot of a ransom payment coming in on a oil ship, oil barge that was hijacked off the coast of Africa. So you can see there are real lives at stake, real dollars at stake. And then this guy, I believe this is a map of energy usage per capita. I don't have the notes in front of me at the moment. I gotta go grab my textbook. But anyway, it's 2:30, so I welcome you to look through the rest of the chapter. We'll pick up chapter 1 and 2 next week. So we've got about 3 hours to get through there. The chapter 1's available if you don't have your book. So just start reading through it. Tim's going to work on making the exams a little user-friendlier this semester, so there aren't quite as many questions and clean them up. So I think you'll find the exams to be not too bad, more pleasant than previous semesters. So. All right, guys. Well, thanks. I'll see you Tuesday.
Okay.
Yeah.